Right, so we are taking some example here. So in this example that I'm considering, there is a cubical block, means the dimension of the block is same for the all side. This is 40 centimeter, this is 40 centimeter, this is also 40 centimeter, and this block is sliding over an inclined plane which is tilted at 30-degree angle to the horizontal plane. So the velocity of the block is 12.5 centimeter per second, and this is oil, and for this oil, the thickness of the oil between the block and this plane is 0.005 centimeter. The weight of the block is 4.5 Newton. Now in this case we want to calculate the viscosity of this oil. So to calculate the viscosity of oil, as our previous discussion in this lecture, we know the formula, that is tau is equals to mu du by dy. Right, now in this case mu is unknown. So first of all we consider this one, stress, shear stress. So according to our definition, shear stress is force upon area. That is shear force. So the shear force is the force which is acting tangentially to the surface. So if I am taking the 2D view of this picture, so I can draw like that. So this is our block, which every side is 40 centimeter. This is the plane, that is fixed one. This angle is 30 degree. Now as we know, the weight of this block is acting in this side. Right, now if we will draw a line parallel to this inclined plane and perpendicular to this inclined plane, in that case the angle between this weight and this perpendicular line will also be 30 degree. So the force which is responsible to move this block with this velocity is along this line, that is parallel to this surface area. So we know if we resolve W along this perpendicular line, this will be equal to W cos theta, that is cos 30 degree, and along this line this will be W sin 30 degree. So the force which is responsible to the moment of this block is W sin 30. So we know this one. So this force is W sin 30. Alright, and the surface area is the block surface area, this one, this part, this is the area. So we know this is a cubical block, so in this case the area will be 40 into 40. So centimeter, I'm converting this in meter, that is 0.4 into 0.4. So W is 4.5 into sin 30 divided by 0.4 into 0.4. So this value of W sin 30 we can calculate from this side. Alright, so we know this one. So this is completely known. So the tau is known. Now this is unknown. Now the next term is this one. So for the calculation purpose, I'm saying that is this velocity gradient is a linear profile. What is the sense of linear profile? So means, if we are saying there is an oil layer between the block and the solid surface. So let I'm drawing in the larger part. So let I'm saying this is the inclined plane line, and here is the block, and this is the fluid layer, that is the oil, and this, let I'm saying T, and let I'm saying the block velocity is V. Alright, so as we know the block velocity, we know what is the thickness between the block and the solid surface. So we can say that there is the oil layer which is exactly stick to the solid surface has zero velocity. Means the oil layer which is stick to this layer has zero velocity, and the velocity of the layer of oil which is stick to this block is exactly equals to the velocity of the block. So means for this layer that is stick to this block, the velocity is V. So means there is a profile here, there is a distribution of velocity here. At this point the velocity is 0, at this point the velocity is V, and for the calculation purpose we are saying this is linear, so the profile will look like this one. This velocity vector is V, this is something, and this is 0. Alright, so means if you want to calculate the velocity distribution over the distance perpendicular to the fluid flow, that is in this direction, that is actually we want to calculate the velocity gradient. So we can say that the du upon dy is equals to, du is the difference in velocity, so here the velocity is V, here the velocity is 0, so we can say that this is V minus 0 dy. The perpendicular distance in the flow direction is T, so this is T here, so actually this is V by T. So what is V? V is 12.5 centimeter per second, so we can write this is 12.5 into 10 to power minus 2 meter per second, and thickness, that is dy, that is also given here, 0.005 centimeter, so this is 0.005 into 10 to power minus 2 meter. So this is our velocity distribution. So now from this formula we know tau and what is the velocity gradient. So mu will be equals to, so mu will be, or let I'm writing like that, tau is 4.5 sine 30 degree upon 0.4 into 0.4 is equals to mu, that is unknown for the oil, into du upon dy, that is 12.5 into 10 to power minus 2 divided by 0.005 into 10 to power minus 2. So the mu of oil will be, let me calculate, so this value will be around 0.0056 Pascal second, or in terms of poise this will be equals to 0.056 poise. Alright, so means for the calculation purpose we will take this velocity gradient is linear like that. Okay, so in the previous case or previous example we consider that is the du upon dy we are considering linear, that is the velocity variations over this distance t is linear. Now in this next example we are considering this is not linear, or I am saying it has some parabolic profile. So in this my example I am saying there is some solid surface, there is some fluid is flowing over here, and the fluid height above the solid surface is 20 centimeter, and the topmost layer velocity is 100 centimeter per second, and I know the viscosity of fluid, that is 8 poise, or we can also say that this is also equals to 0.8 Pascal second, as we know the conversion, that is 1 poise equals to 0.1 Pascal second. So 8 poise also equals to 0.8 Pascal second. So in this case that I am saying the distribution of velocity over this distance, that is normal to the fluid direction, this is the fluid direction, fluid flow direction, normal to the fluid flow direction is not linear, it's parabolic, right? It's parabolic. So in this case I want to calculate the du upon dy, that is the velocity gradient at y equals to 5 centimeter and du upon dy y equals to 10 centimeter and du upon dy at y equals to 15 centimeter. Similarly, I want to calculate shear stress at y equals to 5 centimeter, shear stress y equals to 10 centimeter, shear stress y equals to 15 centimeters from the solid surface. So let I'm saying this point is 5 centimeter, this point, that is a midpoint, this is 10 centimeter, and around here I am saying this is 15 centimeter above the solid surface, and I am saying this velocity variations is not linear, it's actually parabolic. So for the parabolic function or parabolic equation, if I want to write the equation, we can write that is u, that is the velocity, is the function of y. So let I'm saying this is y direction, this is x direction, so this is x, this is y. So u is the parabolic function. So that I'm saying that is u equals to a y square plus by plus c. This is a parabolic equation. If I'm saying this is linear variations, so we can write that is u is equals to ay plus b. So u is the linear function of y. Now in this case u is the parabolic function of y, square terms. So I'm saying that is u is the parabolic function of y here. So in this case I have three constants a, b and c. So to solve the three constants we require three boundary conditions. Right, required three boundary conditions. So let I'm saying first so I need first boundary condition. So what is the first boundary condition? So as we know, the layer which is exactly at the solid surface, at the surface, has zero velocity. So we can say, because this is u equals to 0 because of no slip condition. So we can say that at y equals to 0, u is also 0. So I'm saying at y equals to 0, u is also 0. So I'm putting this value in this case. So as putting y equals to 0 here, so this whole term is 0, this is also 0, u is also 0. So I can write there is c is equals to 0. Alright, this is our first boundary condition. First boundary condition. What is second? I know the boundary condition. What is the second boundary condition? That is, I can say that is at y equals to 20 centimeter. I know the velocity. Here the velocity is 100 centimeter per second. This is also known. So I can say that at y equals to 20 centimeter, u is 100 centimeter per second. So putting this value in this case, so I can say that u is 100 equals to a, y is 20, that is 20 square, b, y is 20, plus c, that is 0. From this calculation, c is 0 here. So from this case, this equation, solving this equation, you can write 100 is equals to 20 square is 400 a, then 20 b. This is our second equation. Alright, so beginning second equation, but in this equation we have two unknowns. That's why we require third boundary condition. So we know third boundary condition. So what is the third boundary condition? Now, as our previous discussion, we know as we are moving from the solid to top layer, du upon dy is decreasing as we are moving this side. So at the top layer, at this layer, du upon dy, that is velocity gradient, will be 0. At the solid surface, velocity gradient is maximum. At the top surface, the velocity gradient is 0. So my third condition is at y equals to 20 centimeter, means at top layer, du upon dy is 0. Alright, so to calculate du upon dy, we know what is the equation. U equals to ay square plus by plus c. So we know that is u is equals to ay square plus by plus c. So du upon dy, differentiating this term u respect to y, we know that is twice of ay plus b, y single here, and c will be 0. So we know the equation. So from the boundary condition, at y equals to 20 centimeter, du upon dy is 0 here. So from this equation we can write this du upon dy is 0, twice of a, y is 20 plus b. Alright, so this is our second equation. So what is our second equation? Second equation is 40 a plus b, a plus b is equals to 0. This is our second equation. This is third equation. So from our second and third equation, we have two equation and two unknown. We can simply calculate the value of a and b. Alright, we can simply calculate the value of A and B. So by the use of these two equations, equation 2 and equation 3, this is our equation 3 actually. By the use of equation 2 and 3, we can calculate the value of A and B. So that I'm solving this equation. So I'm getting the value of A is equals to minus 0.25 and the value of B is equals to 10. Alright, so by solving these equation 2 and equation 3, we are getting A is equals to minus 0.25 and the value of B is 10, and from our first boundary condition we know what is the value of C, that is 0. So we have the value of C, we have the value of A, we have the value of B. So we know all the values. So putting these values in this equation, we know what is the exact velocity profile. So here we can write that is U is equals to, just a minute, pen is not working actually. So we know the value of A, we know the value of B, we know the value of C. So we can write U is equals to, so value of A is minus 0.25, so this is minus 0.25 y square. I'm putting the value of A is here, so this is y square, plus value of B is 10 here, this is 10 y, and C is 0. So this is the profile of velocity, that is U is equals to minus 0.25 y square plus 10y. Right, now, so we know the profile. Now I want to calculate the value of du upon dy at y equals to 5 cm, du upon dy at y equals to 10 cm, du upon dy at y equals to 15 cm. So I know what is U. So U is minus 0.25 y square plus 10y. So I think we can calculate du upon dy by differentiating U with respect to y. So what is the value of this one? So I think this is twice of this value, so this is minus 0.5 y plus 10. Alright, so now to calculate the value of du upon dy at any distance from the solid surface, that is y, we can provide the value of du upon dy. So let first I am saying at the 5 cm. So at the 5 cm, the value of du upon dy is, so that I am calculating this value is 7.5 per second. This is meter per second, this is meter, so this is per second. At the 10, this value is 5 per second. At the 15, this value is 2.5 per second. Right, so we're getting du upon dy at 5 cm, that is 7.5 second, this is 5 second, and this is 2.5 second per second. Similarly we can get this value because we know tau at any y is equals to mu du upon dy at any distance y. So we know, I think, what is the viscosity of fluid, that is 0.8 poise. So we know this value, if we know at particular distance this value, so we can calculate this value. So the value of shear stress at a distance 5 cm from the solid surface is 6 Newton per meter square. At the 10 cm, this value is 4 Newton per meter square, and at distance 50 15 centimeter from the soil surface is 2 Newton per meter square. Alright, so these are the values in this case. Now if I want to calculate du upon dy at distance y equals to 0. So similarly, when I am putting the value of y is 0 here, y is 0 here, so in that case the value of du upon dy at the 0 will be what? Shall be 10 per second. So the value of tau at y equals to 0 will be, it's 8 Newton per meter square. Alright. Right. So we'll see some more properties in the next lecture. Till then, take care of yourself. See you in the next lecture. Thank you.